The last video got kind of crazy. You could tell it's kind of crazy if you just look at these notes right here. How is a student supposed to make any sense of these different graphs and all these different concepts floating around here? We need a summary. I'm going to start this video with the summary. A key idea that I wanted you to get from the last videos is that the function is increasing if and only if the derivative of that function is positive. Similarly, a function is decreasing if and only if its derivative is negative. And a function is flat at a point that we'll later refer to as a critical point whenever the derivative equals 0. These were the concepts of the first video in this section, which probably made a fair amount of sense to you. The concepts of the second video, which probably got a little bit out of hand, is this idea of concavity. A function is concave up whenever its derivative is increasing. So not when its derivative is positive, but when its derivative is increasing. But we can talk about when a derivative is increasing by thinking about the second derivative, because increasing is referring to the rate of change of the derivative. The second derivative talks about the rate of change of the derivative. A function is concave up if and only if its derivative is increasing, if and only if its second derivative is positive. Similarly, a function is concave down if and only if its derivative is decreasing, which happens if and only if its second derivative is negative. And just like we have a special word for when the function is flat, when the first derivative is 0, we call that a critical point. We have a special word for when the derivative is flat. The derivative is going to be flat whenever the second derivative equals 0. And at that point, we have what's called an inflection point. Okay, this is hard enough and I don't want to get into any technicalities, but I feel a little bit bad lying to you, so I'm going to put this little asterisk here. Inflection points technically don't happen just when the first derivative is flat. They happen when the first derivative switches sign, switches between a positive and negative number. And it's going to switch sign between a positive and negative number when the derivative is flat, which happens when the second derivative equals 0. However, it's possible for the first derivative to be flat, the second derivative to be 0, and us to not have an inflection point, but it's kind of a special case that we don't have to worry about in our class. So for our purposes, maybe ignore this little asterisk, but note that I have to put it in there just so I don't feel like I'm technically lying to you guys. To try to make this as straightforward as possible, we have these 3 vocabulary words: increasing, decreasing, and flat. And the purpose of video 1 is to tie those 3 concepts together with the first derivative. The purpose of video 2 was to introduce 3 new concepts, the idea of concave up, concave down, and an inflection point, and to tie those 3 concepts with the change in the first derivative, which turns out to be exactly the second derivative. What I'd like you to be able to do is look at a function like what's pictured here. Maybe we'll call this thing g of x, and be able to tell me when this function is increasing, decreasing, flat, concave up, concave down, and where it has inflection points. Let's start with low-hanging fruit. Let's start looking for increasing, decreasing, and flat. A function is increasing when it goes up as you read this thing from left to right. So all throughout here, this graph is going up as I read it from left to right. Now it's going down, so I'm going to ignore that part, but then over here it's going up again. It looks like my graph is increasing from negative infinity all the way up to negative 1, and then again from 4 up to infinity. When is the function decreasing? Well, it's kind of decreasing when it's not increasing. It's decreasing in here from negative 1 to positive 4. And that takes care of just about everything, although if you're really nitpicky, you might argue that at negative 1 and 4 itself, the function is neither increasing nor decreasing. It's flat. At these points where I switch from increasing to decreasing, where the function is flat, we have what are called critical points. In this case, my critical points come at x equals 1 and x equals 4. But what about concavity? Can I look at this graph, g of x, and talk about where it's concave up, where it's concave down, and where it has inflection points? Well, remember, concave up, loosely speaking, means it kind of has this bowl shape. Think about like a cereal bowl or something. And concave down is that same bowl when you get it out of the dishwasher and you're trying to dry it and you turn it upside down so that all the water leaks out. So where does this graph look like an upside down bowl? Well, it takes a little while to get comfortable with it, but maybe you can see that on this interval in here, all the way until, I don't know exactly where, somewhere in here, it kind of looks like an upside down bowl. And then over here somewhere, it kind of looks like a right side up bowl. It's hard to tell where exactly it switches from concave down to concave up, but it kind of looks like it happens somewhere in here. Upside down bowl, right side up bowl. Concave down, concave up. If I had to guess where it switched, I don't know exactly, somewhere in here, maybe roughly 1.5. To the left of this point, way over here, I'm concave down. Think upside down bowl. And to the right of this point, I'm concave up. But is it exactly 1.5? I mean, it's really hard to tell just by looking at the graph. Maybe I should confirm all this stuff algebraically. Well, fortunately, I know the equation of this function. The original function that was pictured is 2x cubed minus 9x squared minus 24x plus 5. So what can I do with that? Well, if I knew the first derivative, f prime of x, which is easy enough to find because this is a polynomial, it's what, 6x squared minus 18x minus 24? I could figure out when the function is increasing and decreasing. I'm pretty sure I already know when it's increasing and decreasing, but maybe I should go through the exercise. Let's figure out when f prime of x equals 0. F prime of x equals 0 when 6x squared minus 18x minus 24 equals 0. And if I were solving this equation, maybe I'd recognize that all three of these terms are divisible by 6. So if I divide both sides of the equation by 6, I get x squared minus 3x minus 4 equals 0 divided by 6, or 0. And then maybe I'd be really happy because I'd recognize that, hey, this factors. I can rewrite this as x minus 4 times x plus 1, because negative 4 and positive 1 are the two numbers that multiply to negative 4 and add to negative 3. So x squared minus 3x minus 4 equals 0 is the exact same as x minus 4 times x plus 1 equals 0. And x minus 4 times x plus 1 is going to equal 0 when x minus 4 equals 0, or when x plus 1 equals 0, which happened at 4 and negative 1 respectively. Oh yeah, that's exactly what I saw on the graph right here. The graph of my function is flat at negative 1 and at positive 4. If I wanted to figure out when f of x was increasing, what I'd have to do is figure out when f prime of x is greater than 0. And the way I would solve that inequality, 6x squared minus 18x minus 24 is greater than 0, is by doing my little sign line trick that I did before. I'm going to take my number line, which is supposed to be pictured here, and divide it at negative 1 and again at positive 4, and recognize that that creates three different regions, region 1, region 2, and region 3. I'm going to take any number I want from region 1, and I'm going to plug it into f prime of x. So I don't know, f prime of negative 2 maybe. If I take negative 2 and put it into this machine right here, negative 2 squared is 4, and 4 times 6 is 24, and negative 2 times negative 18 is 36. So I get 24 plus 36, which is what, like 60 or something, and subtract 24, and I don't really even care what the value is, because all I care is that that's going to end up being greater than 0. F prime of negative 2 is greater than 0. What that means is negative 2 is in my solution set, and what that means is all of the numbers in region 1 are in my solution set. If I did the same argument with f prime of 0, I'd see that f prime of 0 is less than 0. If I put 0 into this machine, negative 24 comes out, and therefore 0 is not in my solution set, so none of the numbers in region 2 are in my solution set. I do this one last time with any number I want in region 3, maybe f prime of 5, and when I plug 5 into this machine, what you'll see is that a positive number comes out. I don't even want to do the calculation, but it happens because 5 squared is 25, and 25 times 6 is so big, 150, that when I subtract 18 times 5, which is 90, and then 24 more, I'm still at a positive number. F prime of 5 is greater than 0, therefore all numbers in region 3 are in my solution set. The solutions to this inequality are all the numbers in region 1 and region 3, and the numbers in region 1 and region 3 are the numbers that are less than negative 1 and greater than positive 4 respectively. My function is increasing on this interval and also on this interval. You're like, right, but what about concavity? That's the one that was really hard by looking at this graph. Well, we can do the same analysis. We just don't look at the first derivative, we look at the second derivative. And the good news about the second derivative is it's easy enough to find. All you gotta do is take the derivative of the derivative. We already know f prime of x is 6x squared minus 18x minus 24. Take the derivative of that, and you get 12x minus 18. A nice, easy to deal with function. You want to know where you have an inflection point? An inflection point happens when the second derivative equals 0, loosely speaking. Here's my second derivative. I'll set this thing equal to 0, and I'll solve. 12x minus 18 equals 0. Add 18 to both sides. You get 12x equals 18, divide both sides of the equation by 12, and you get x equals 18 twelfths, which reduces to 3 halves. What that's saying is I have an inflection point at 3 halves, in other words, 1.5. It's almost like I knew that was going to be there, like I was the one that made up this example or something. And that's the point where I switch from concave down to concave up. If I consider the second derivative of any x value that's less than 3/2, I'm going to get a negative number. Don't believe me? Try it. Consider, 0 for example. Put 0 into this machine. 12 times 0 minus 18 is negative 18. The second derivative at 0 is negative. When the second derivative is negative, that means your derivative is decreasing, which means your function is concave down. My function is flat. In other words, I have critical points when f prime of x equals 0, which happened at -1 and +4. My derivative is flat. In other words, the second derivative is 0 when my function has inflection points, and that happens at 3/2. My function is concave down to the left of 3/2, and my function is concave up to the right of 3/2. And I can confirm all that by doing one more sign line, except now not looking at the first derivative, 6x squared minus 18x minus 24, but instead looking at the second derivative, 12x minus 18. If I want to know where my function is concave up, for example, I have to figure out when 12x minus 18 is greater than 0. To solve this inequality, what I could do is solve the corresponding equality. My solution is 3/2. 3/2 breaks my number line up into two different regions, the numbers to the left of 3/2 and the numbers to the right of 3/2. If I pick any number I want to the left of 3/2, any number that I want in region 1, 0 for example, and I put that into the second derivative, a negative number comes out. What that means is 0 is not in this solution set, and what that means is that none of the numbers in region 1 are in this solution set. Pick any number I want in region 2, 2 for example. Put 2 into the second derivative. 24 minus 18, or 6, comes out. 6 is greater than 0. What that means is that 2 is in my solution set, and what that means is all the numbers in region 2 are in my solution set. The interval on which the second derivative is greater than 0 are all of the numbers to the right of 3/2. My function is concave up from 3/2 up to positive infinity, as we see with the graph right here. Lots of ideas, pretty challenging. We're going to do one more example just to try to hammer this stuff home, but that'll happen in the next video.